All right, let's continue where we left off. So in part one of the recording, I showed you the basics of an FPGA, what its basic components are, what its basic architecture is. But let's just spend a couple of slides talking about some of the big picture questions. Why would you use FPGAs? Under what circumstances are you going to use FPGAs? And I guess the best thing that the FPGA gives you, the winning factor, would be that flexibility, that ease of programming and debugging and reprogramming it. And of course, I mean, in terms of performance, it gives you a good mixture between your ASIC, which is ASIC and full custom, which is the best performance, down to instruction set processors that could be very slow in implementing a specific applications. So in terms of ASIC, obviously, I mean, you would design something to do, let's say, floating point division, right? Or some other some filtering algorithms that would require a combination of operations that you want to do. And then in ASIC design, basically you have a team of designers who make a circuit specifically for that task, and that circuit can't do anything else. And of course, it's going to be the fastest. With FPGAs, you have a fabric that is meant to be as general as possible. So if someone wants to do, um, integer multiplication, they could do it. If they want to do 100 parallel additions, they could do it. Text searching, DNA matching, everything, right? So the FPGA has to be able to cater to all these different applications. And of course, to do that, you need to provide programmability within the interconnect as well as your functional units. And programming within the interconnect means that you have to add pass transistors along the way of the signals, which significantly degrades the performance compared to ASIC. But again, compared to instruction set processors and DSPs, it could be faster, and the keyword is could. So if your ISP, for example, does have instruction set processor, does have a floating point division unit, great, you can do a floating point division very quickly. If it doesn't, which does happen with a lot of simple microcontrollers, then you have to build it up through integer operations, and one simple well, not simple, but one division, one floating point division could entail 2,000, 3,000 instructions. So if you map the floating point division operation onto the FPGA with all the bells and whistles that you need in hardware, even though it's going to be much worse than an ASIC or much worse than an instruction set processor that does implement floating point division in hardware, it's going to be much faster. The FPGA is going to be much faster implementing the floating point division compared to an ISP that does not have a native floating point division operation, right? Now, I talked about, floating point division operation here, but plug in your favorite application, DNA sequencing, any kind of, filtering, image processing. And if your DSP chip or ISP was not specifically built for that, you have to put together a bunch of instructions that do that, go through the sequence of instruction decoding and so on and so forth. So in terms of performance, it's going to be worse than FPGAs. But then in terms of flexibility, again, ISP is going to be much better than FPGA because you just change a couple of lines of C or Python or what have you, and then you compile it and run it instantly. With FPGAs, it's not as flexible. I mean, writing code in Verilog VHDL, even System C, is not as easy as writing Java on ISPs. And also, if you want to do if you look at the development, debugging, and testing cycle, with FPGA you have to wait for maybe a day to place and route the design, so it's not going to be as easy to use as ISPs. Um, I guess I can skip this slide. You can read it later, but basically time to market and flexibility would be an issue. The other issue that I want to just mention would be the DSM issue. So with newer technologies, you have more and more of these deep submicron issues. variability and so on. With FPGAs, which by the way are usually the first chips that come out of new fabrication nodes, and they're big and has implemented a lot of gates, is that in FPGAs you have a modular design. You have a tile of the FPGA that you design, you simulate it very in a lot of details. And once you know that there are no issues, then you just replicate that tile, make an array, and bingo, you have your FPGA. Now, in terms of the performance gap that I alluded to earlier, there was this very early study in 2002 that looked at a couple of designs, mapped them to the FPGA, mapped them to the ASIC, and compared the results as the technology progressed, right? So 90 nanometers is now ancient history, but the trend, even though the numbers might be different, but the trend still does hold. So here in picoseconds, it shows the FPGA delay, and look at the numbers: 200, 400, 600. And here in picoseconds, you have 10, 20, 30. So, anywhere between 10x to 20x difference between the performance of the FPGAs. Later studies by Jonathan Rose's group in 2006 looked at a bunch of applications. And of course, I know this is not an eye exam. It's probably not visible in the video. Feel free to take a look at the slides that I posted on the Moodle page, or go to the paper and read it. But basically what they do is they look at a bunch of designs. And modern FPGAs don't just have logic. They do have some DSP blocks that do multiplication, multiply, accumulate operations. They do have some logic and memory. And basically, if they use these new features of the FPGAs, then the area ratio, and the area is the silicon footprint that you need on FPGA to implement it, as opposed to ASIC. It goes down from a 40x worse FPGA compared to ASIC down to 21x worse, which, I mean, 21 seems like a very, very large number, but if you consider the flexibility that buys you, then it doesn't seem to be that much higher. And then the next table talks about the delay ratio. And you can see that FPGAs could be there at 2.1x compared to ASIC, which is pretty good. I mean, compared to 2002, in which you had 20x, 10x, coming down to 3 or 2 was a big step forward. And of course, I guess I don't remember the numbers. I think ASIC compared to full custom itself is 5x to 10x gap. So, you know, that shows the perspective. And then the dynamic power consumption ratio, anywhere from 12 to 9 would be what the FPGA has. And of course, I mean, these were the FPGAs that they used here are not the low power grade FPGAs. So you could go significantly lower than this if you use specifically the low power applications of the FPGA, but that probably means that the delay is going to go up. So in terms of delay in area and power, the main culprit here is the programmable switches, the programmability of the device. So on one hand, you do like programmability because your time to market significantly decreases. So from this row to this row, things are increasing, as I have shown here. So time to market FPGA is much better. In terms of cost, FPGA is much better, but in terms of performance, ASIC is much better. Right? So that's basically the programmability is a curse and a bonus at the same time, and a blessing at the same time. So you have to look at the application. And as time goes by, more and more designs do become, I mean, it makes sense for, places like Cisco and so on to use FPGAs in their actual designs because the performance of the FPGA is improving significantly. So just to recap again on what the FPGA looks like in a very, very simple model that I'm going to show you now. You have an array of logic blocks, or functional units as they're called, and the routing infrastructure. And I'm going to dig a little bit more deeper on how these are made and how you can implement logic in them. So basically you would have a chip similar to, this, for example, the Xilinx chip that you might have, and that chip does have, at its core, does have a bunch of programmable routing structures shown in green here, and some of the programmable lookup tables, or LUTs as they are called in the FPGA terminology, which are shown in green here. And in the next couple of animation steps, I'm going to show you each of these, the interconnect and also the logic, how they're implemented. So if you think about these lines here, think of these as wires that are electrically not connected to other wires, as I talked about in the example of F1, F2, F3 that I showed you in the previous slide. And basically what you have is you have intersections. So one part of the interconnect structure is the wires themselves. The other part is what is called the switch box, which decides which one of these connect to which other ones. And I'm showing you one common way of making connections. So basically if you number these tracks as 1, 2, 3, then 1 only connects to wire tracks 1 on every side, 2 connects to 2s, and 3 connects to 3s only. So you can't have a connection going from 1 to 3, for example. This is not provided because the cost would go up dramatically if you wanted to provide that. And now inside each of these diamonds, you could have pass transistors here. This is the old model. Today's FPGAs don't use pass gates like this. They use mux structures, but the basic principle is the same. And each of these 6 circles here provide you an independent switch that could make a connection between each of these. So you could potentially have a signal coming this way, and by turning on the switch it would connect to this. By turning on this switch it would also go in here, right? So this could be a gate providing input to these 2 gates, and then this one could be left unused. Or I could just have a signal going in here, coming out here, and I could have another signal going in here, going through this, and coming out here, right? So you could have independent copies, or one line going horizontally carrying one signal, another line going vertically providing another signal. And you could have, fan outs, branch outs at these locations. So usually how these were implemented in the old days were just a pass transistor connected to its gate, connected to an SRAM cell. And if you write a 1 or 0 into this SRAM cell, then you can make the decision of whether or not this line is connected or not, and you would have a tree of interconnects. And later people started adding buffers too in these connections, and because of the buffers, then you had some wires going in this direction and some others going in the other direction. So basically you have to look at one-way connections in the later implementations. Later on, what happened was that they said maybe a better, smarter way of using the resources, because you don't want to use too many of these SRAM cells, is for this particular line, this line could be connected to a mux that says my input comes from any of the other sources, and it doesn't have to be just these 3 locations. A connection could come directly from one of these logic gates into the switch box, and then you could share, you could basically use only 2 bits to control this mux, as opposed to using 4 independent ones to connect all of these connections. Okay, so this is roughly how the interconnect works. There are more details that I'll talk about later, but this is the basic underlying architecture. How does the logic work? Well, the logic, and of course, the other thing that I didn't show you is you would have something similar to this, connecting these tracks into these logic blocks. That's called connection box in some of the older technologies, but again, this could have a direct connection from the logic inputs to what you have in here. Now, again, another simplified version of the logic itself then is going to be a lookup table here, right? So you could have a connection box that could be a full crossbar, meaning that any of these lines has the option of getting its input from any of these wires coming in, right? So you would have a fully populated switch box, unlike what we had, the diamonds that only happened on the diagonals of the switch box. So if XYZ can come from any of these wires, and if the output of the lookup table could go to any of these wires, then you have a flexible architecture in which you can route things. And I don't want to, get into too much details, but it's hard to resist. So if, for example, you have this much flexibility in the connection box that you can connect anything to anything else, then it shouldn't really bother you much that you can only connect from one to one, track 1 to track 1 in the switch box, because if you want to route the signal to track 2, all you need to do is to see where did this come from. Let's say it came from this guy. Sorry, that can't happen. Came from this guy here, right? And then switch it to track 2, and then everything is going to now translate to track 2. So if you have enough flexibility in the connection box, that means you can have less flexibility in the switch boxes that you have. Now, how does this lookup table implement a function? Well, basically it's a RAM, right? If I have a RAM, and here I'm showing you a lookup table with 3 inputs, the most common size for the lookup table for a long time used to be 4 input lookup tables, but nowadays it's 5, 6, and 7. So the size of the lookup table has increased, but again, the basic principle is the same. So let's look at a 3 input lookup table, which is also called a 3-LUT. 3-LUT. Now, in a 3-LUT, XYZ could be the address lines. So this part would be the address decoder, and here you would write 0, 1s, and so on in this truth table and get the function f, right? So if you want to, for example, have an AND gate, then you would write 0, 0, 0, all zeros except the very last one, right? So only when XYZ are all ones, this line will be connected and routed to the output, and you get your output. Otherwise, the output is going to be 0, right? So you basically write the Boolean a truth table into this, and you have a function. And as I said earlier, it doesn't really matter how complex this function is. The 3 inputs x, y, z could go to an, when you draw it on the paper, when you do the schematics, this could be an XOR feeding an AND gate followed by a NOT gate. It could be, redundant, many logics, but you don't care. You just get the truth table of that, put it in here, and this lookup table can implement any function of 3 inputs, and that's how the FPGA works. So I think I already talked about this stuff and the question of how you want these programmable switch elements, which by the way could be anti-fuses or fuses, as I mentioned earlier, but I'm not emphasizing them because they are not the dominant versions of the FPGAs. Now, in terms of the routing channel, so I did talk about the intersections, how these wires are connected, but the wires themselves you do need to make some design decisions on them. Now, one choice would be to use fixed channel width. So if I go back, if I go back here, now the connections here could be from each of these green boxes to the next green box with a wire that gets disconnected, right? Now, the good thing about this, which is also called a one segment routing tracks. So the length 1 routing tracks are good because they're flexible. You're not going to waste any of the segments that you have, and it can make any connection to any other connection. The problem with it is you have too many pass gates or muxes in the way, which means they are going to be slow, right? So the solution that people came up with was to provide a mixture.